thank you for the invitation to be here. It has been a very interesting webinar since yesterday, with a lot of interesting presentations, and I really have a difficult task in presenting some innovation in extraction processes. So let's hope I can keep up with this high level of the presentations. So in fact, I'm going to present you some of the works that we have been doing on extraction processes, but how can we at the same time innovate and make some changes and take further advantages of the use of NADES in these processes. And for us, it is also important to take a look at food waste and byproducts, as it has been here presented different times. So food waste and byproducts generate millions of tons of food wastes from not only the industrial sector, but also in the restaurants and food services, supermarkets, and also at our homes, which together contribute to nearly 10% of the greenhouse gases emitted by the planet. So this is definitely a problem that needs to be tackled. And also in the concept of the circular economy, there may be also value in this waste, as of course this agro-food industry waste or byproduct, they are rich in several components that can be used for other products, other high added value products. And how can these be tackled? Either by the bio-refinery concept, as we have heard here as well, and also the extraction of bioactive compounds. And we are all familiar that still the conventional extraction using organic solvents is the most widely used. However, this is changing, and this perception is changing, particularly in the cosmetic industry, where new products are already being launched with the use of eutectic systems in their final composition. So the idea is to develop a sustainable process based on an eco-friendly technology using green solvents that comply with the green chemistry matrix, that result from renewable sources, which are these natural deep eutectic systems, in order to extract bioactive components, but also at the same time use these in their stabilization, and also in some cases to be able to purify to a certain extent these extracts. And what we aim is to explore the bioactive or therapeutic properties of these extracts. So how can they be used for, how are they better, and how can we take advantage of these? Because if we are just extracting for extraction, then at a certain moment we start questioning, but why are we doing this? So definitely there needs to be a purpose on this. And all of us know that designing these processes, we can have a higher selectivity, design safer products with a lower environmental impact, reducing the energy consumption, using renewable natural products, and eventually providing high quality extracts to different industries. So in Portugal, we have been focusing mostly on the byproducts that are most relevant for us. And this is the work plan of Marta Marques in collaboration with Décio Lúcio. So she's the first PhD student that we have in collaboration with the company. And she's looking at different residues. The orange peels, which are account for the peels, the seeds, and the pulp of the citrus fruits, account for half of the weight of the fresh fruit, and these are still rich in bioactive components. The same happens for apple pomace and grape pomace, which account for nearly 20% of the fresh fruit weight. And we can recover different types of bioactives from these byproducts. So from the orange peels, the most known is the essential oils from limonene, but we can also extract pectin or other glycosides with different bioactivity properties. From the apple pomace, we can extract some vitamins and also some natural antioxidants. While the grape pomace, on the other hand, it has been extensively studied by different extraction technologies, and we can extract different phenolic acids, but also flavonols, proanthocyanins, and other anthocyanins. So as a preliminary work, we have used orange peels, alcobaça apple pomace, so a typical apple from Portugal, and grape pomace. So we tested different DESs using the same extraction conditions, and our aim was not only to observe this, the ability to extract the phenolic content, but we want to go a little bit further, and we want to test and implement these screening assays for the bioactivity of the extracts. So instead of doing the conventional DPPH assay for the antioxidant activity, we are implementing the reactive oxygen species, the ROS test, using model cell lines. In this case, we use CACO2 cell line, which is a model for intestine cells, and in the presence of our NADES plus the extract, we will see what is the effect in these species. Note that we don't want to purify the extract or to obtain the extract without the NADES. So our intention is always to use the NADES in the final formulation and use it as a bioactive solvent as well. Additionally, we aim to do the anti-inflammatory activity by the procedure that we can identify the EL8. This is a standardized protocol that we are implementing. So for today, I wanted to show you the results, the first results that we got on the reactive oxygen species for the orange peel extracts and grape and apple pomace for the different DESs. So as a control and using our DESs, we don't see major differences, but when using, interestingly, orange peel or apple peel in a lower concentration, we get a reduction in these reactive oxygen species. I remind you that this is just preliminary work, so Marta has just started, and I hope that in the next meeting I will be able to show you not only the final results of these, but also some work on the anti-inflammatory activity, but also on the anti-proliferative activity and cytotoxicity of these extracts. So some of these molecules are also known to have anti-cancer properties, and what we aim to do is to see if there is a therapeutic window that enables us to use these molecules as anti-cancer agents. Another very important byproduct that we have in Portugal comes from the fishing and canning industry. This is a large industry in Portugal, and more than 50% of the waste from the canning industry includes different tissues like heads, skins, viscera, and this represents a very huge burden for these industries. So this is the work that has been carried out by Miguel Batista in collaboration with IBET. So I'm co-supervising his PhD, and what we did was try to evaluate if it was possible to apply NADES for the extraction of collagen from blue shark skin. Blue shark skin is a species of shark that exists largely in Portuguese coast, and it's used for different purposes, and their skin is rich in collagen. So the conventional approach to extract collagen from shark skins is to make a pre-treatment with sodium hydroxide for 48 hours and followed by acetic acid extraction, so an acidic extraction of collagen for another 48 hours. After this procedure, the collagen is precipitated, it is purified by dialysis and freeze-dried for the obtention of the powder. So our approach was to see if we could use an acidic DES for the extraction of collagen. We didn't perform any pre-treatment step for the extraction of the proteins, of other proteins, and we simply proceeded for the NADES extraction. And as you can see here, we performed the extraction for 1 hour at 40 degrees. And afterwards, we separated, in this case, if we want to obtain the pure collagen, we can separate the collagen from the DES by dialysis and then freeze dry the aqueous extract and obtain the collagen powder. We have performed several analytic techniques such as circular decreasing, FTIR, SDS page, and amino acid content analysis, which is described in this paper. I'm not going to go into detail in here. And we can see that we can have a highly pure collagen obtained, but most importantly is that you can see the decreasing time that is necessary to obtain this collagen. So instead of 48 plus 48 hours, so 4 days of extraction, we reduce this to 1 hour of extraction. This is highly relevant when we are intending industrial applications and scaling up of the process. But not only this is a major breakthrough in this extraction, we thought about using this collagen for biomedical applications. And for that, we wanted to prepare aerogels. This was a collaboration between Miguel and the Technical University of Hamburg with a group of Professor Pavel, who are experts, and Professor Irina Smirnova, who are experts in aerogel production, but they had some problems in the preparation of aerogels from collagen and other natural biopolymers. And this is because of their low solubility in certain solvents. So what we tested here, what Miguel tested here, was the possibility to prepare these aerogels using NADES as the solvent. So collagen that was incorporated in the same NADES as the one that was used for the extraction. This system could be jellified, and following the gelation process, we need to have a solvent exchange in order to go from a hydrogel to an alcohol gel and to be able to dry this alcohol gel using supercritical carbon dioxide. So we are always trying to use green processes, so that's why we are also using supercritical carbon dioxide for the drying of the aerogel. So as you can see, we have a fluffy structure from collagen, and depending an important step in this process is the solvent exchange. So different types of solvent exchanges. If we exchange the solvent from the NADES to methanol just by placing this in 100% methanol, or by making a stepwise extraction, or by making these at different temperatures, we can see that the textural properties of the aerogels that we obtained are significantly different. This can be very interesting in order to tune the properties that we want of our biomaterial. We are pursuing further studies on these to see if these materials are suitable for wound healing, for example, or for the delivery systems, drug delivery systems. But in fact, we see that not only we can extract this material, but we can provide it a different shape that otherwise would not be possible. Another source of bioactive components, rich bioactive components, are aromatic plants. We all know about this, and in collaboration with a large company in Portugal, we are working towards the valorization of their wastes. So plants that are not they cannot sell, or when they have to cut the plants, there is a lot of waste that is generated, and we can create value from these waste. We can create new products for their portfolio. This was what happened. We started by working with salvia, that is an aromatic plant with different bioactive properties, and is a rich source of bioactive components. It is particularly rich in rosmarinic acid, carnosol, carnosic acid, and ursolic acid, as you can see here, and each of these components has different interesting biological activities, such as antimicrobial, anti-inflammatory, anti-cancer activities, but also antifungal activities are among the important bioactive properties of these agents. So we tested a series of different DESs, both by heating and searing and ultrasonic assisted extraction. And we see that there is clearly a difference between using a hydrophilic system and a hydrophobic system. So, for example, rosmarinic acid was not detected in the menthol-based extracts, so in the hydrophobic extracts. So what was our approach, and this was already discussed here and presented here, was to follow a biphasic approach and try to have two different phases enriched with some of the components. So we tested different combinations of the hydrophobic and the hydrophilic DESs. And in fact, we can see that we can have an enriched phase in non-polar compounds, such as carnosol and carnosic acid, and another one enriched with high poly compounds, such as rosmarinic acid. But what I want to point out here from these graphics on the right-hand side is that if we make the biphasic extraction, the profile is completely different than if we make one-phase extraction. So in fact, having both phases at the same time really promotes that one phase is enriched in one component and the other is enriched in the other component, which is highly interesting for the bioactivity studies that we want to pursue. So at this moment, we are carrying out some studies in collaboration with the University of Porto, as it has also been described in the literature that these molecules may have some activity towards some enzymes that are related with Parkinson disease. So again, I hope that I can show you these results in another communication in the future. And just another example that I want to point out, and which has been a hot topic in Europe these last years, is the exploitation of cannabis for medical purposes. So at the moment that we started to work on these, there were only 2 papers reporting the extraction of bioactive compounds from different cannabis species, one with hydrophilic DESs, another one from hydrophobic DESs, but we found that it was very difficult to compare the results that were presented by the different authors. So we started to test the extraction on the same plant using different systems. So we used hemp, which is a variety of cannabis that possesses a low THC content, which is the psychotropic molecule, active molecule in cannabis. And what we did was to make a screening of different hydrophilic and hydrophobic DESs and compare it with the standard extraction using ethanol. As you can see here in the figure of the left-hand side, there are no major differences in the CBD and CBDA content of the extracts. Perhaps there is slightly higher content in the case of menthol lauric acid, which is probably similar to the extract of ethanol. But what I want to point out again is that other molecules are extracted, and in terms of phenolics and flavonols, the profile is completely different. So when we extract using our DESs, the contents in phenolics is much larger than when the extraction is performed with ethanol. On the other hand, in the case of the flavonoids, the content in these molecules is much lower when we use the hydrophilic components. Well, we were not able to perform these analyses using the hydrophobic systems because they interact with the regions to perform these. So this is something that also needs to be taken into consideration, is how can we develop other methods for the characterization of the systems for future discussion between the groups. I think it's an interesting discussion. So, but not only these, when CBD oils are extracted, there is a high wax content in their extraction. So even when the extraction is performed conventionally, either with ethanol or with supercritical carbon dioxide, wax is always a problem, and it needs to be removed from the final product. what we have seen here is that when using hydrophobic systems, the wax content in the final product is very, very low compared to the ones extracting with hydrophilic systems or with ethanol. So we can avoid one purification step, further purification step, when using these hydrophobic systems. In which concerns the chlorophylls content, I'm sorry, here I don't have the names of the DESs, but I just want to point out that is before and after. It's before or after the winterization process, which is a process that takes place to the purification of the waxes. So to lead to the precipitation of the waxes and to separation of the waxes from the extract. What we see is that in terms of the chlorophyll content, the taller bars are the ones from ethanol extraction. So we see that when using any DESs, the percentage of the chlorophylls in the extract is really, really low. And before and after this winterization process, there are no major differences. So we can avoid the wax extraction and also have very limited chlorophyll content in the extract when using these DESs. So this is highly relevant for the cannabis industry because, of course, the downstream purification processes are sometimes the ones that are most costly for these companies. But not only that, we wanted to enhance the bioactivity of these extracts. So in this case, we tested the antioxidant activity of the different extracts by the DPPH method, and we see that when using proline and glycerol or proline lactic acid, we have a much greater antioxidant capacity, which may be due and may be related to the quantity of phenolic compounds that is present and which is not observed in the other extracts. Neither it is on the extract obtained by conventional ethanol extraction. And we also wanted to observe if we could tune the solubility of our matrix by using these DESs. In fact, we see that when using hydrophobic DESs, we don't see any solubility of the CBD in the aqueous phase, of course, because these molecules prefer to stay in the hydrophobic phase. But when we use the hydrophilic DESs, there is a slight increase in the solubility, and we are pursuing these studies further. So as a take-home message, just to finalize on how can we thrive innovation in extraction using natural deep eutectic systems. So we all know that NADES have numerous advantages in the extraction, purification, and also stabilization, which is something that I didn't mention here, but other presentations have already mentioned this. The stabilization of the active compounds that is much greater when in NADES suspension than if we have the lyophilized form, for example, but also coupling NADES with these extracts for the design of new materials, and particularly using NADES as an active solvent in the final formulation for both stabilization, but also for bioactivity enhancement. So I just want to thank the team that has been working with me to all past and ongoing collaborations as well, and the financial support from the different entities. And thank you for your attention.